Good morning students. Once again I am with a new video. In the previous video I have discussed about relation between electric current and drift velocity, and at the end we got a relation electric current I is equal to NEA into VD. If potential difference V is applied across the conductor, this is conductor, length of the conductor L and its area of cross section is A, then current flowing through the conductor I can be given NEA VD. Students, as you know, what is current density? We have defined current density J equals current divided by area of cross section of the conductor, or current flowing per unit area of cross section of the conductor held perpendicular to the direction of charge flow. So if you divide this relation by A, the relation between current density and drift velocity is going to be NEA into VD divided by area of cross section of the conductor. So A cancels and current density J is equal to NE into VD. This would be the relation between current density and drift velocity of the electron. Again we are coming back towards drift velocity. So students, as we have derived formula for drift velocity of electron in a conductor, VD is numerically equal to E tau divided by M. As you know, if length of the conductor is L and electric field at any point inside the conductor is E due to application of this potential difference, then what can be the relation between electric field and potential difference? By the relation between electric field and potential difference, numerically that relation E is equal to minus potential difference V divided by L. This is by the relation E equals minus dV by dr. In this case you can see potential difference applied across the conductor is V. The distance between two ends of the conductor L. So electric field at any point of the conductor is going to be minus V by L, and numerically the value is V divided by L equals E. Suppose you replace value of E as V divided by L, then formula for the drift velocity VD can be written EV into tau divided by M into L. So this is relation between drift velocity and potential difference applied across a conductor, and this is the relation between drift velocity and electric field. So students, in both the relations you can see you might be asked some conceptual questions related to these two formula. If length of a conductor is increased, keeping potential difference across the ends constant, if length of the conductor is increased, then drift velocity is going to be inversely proportional to length of the conductor. So if length of the conductor is increased, drift velocity of electron in that conductor going to decrease. There is going to be a inverse proportionality between drift velocity of electron and the length of conductor, keeping potential difference constant. If value of the electric field is increased, then what going to happen? Electric field is directly proportional to drift velocity. So with increase in the electric field across the ends of the conductor, the drift velocity of free electrons in that conductor will increase. So there is a direct proportionality between electric field and the drift velocity, and inverse proportionality between length of the conductor and the electric field. Students, in the previous video I have discussed what is Ohm's law, and you know, if a conductor is connected with a cell, applied potential difference between the ends of the conductor is V and current flowing through the conductor I. So Ohm's law states that the physical conditions of the conductor remaining unchanged, then current flowing through the conductor I is directly proportional to V, or we can write V is equal to I into R. In the previous video we have derived a relation between electric current I and drift velocity, that is I equals NEA into VD. This is the relation. Now, value of the drift velocity VD numerically written as E tau by M. Suppose we put this value, or in terms of potential difference between the ends of the conductor, potential difference, drift velocity Vd can be written EV into tau divided by M into L. Suppose we are putting value of drift velocity from this relation in equation number 1, that is relation between electric current and the drift velocity, we can get current flowing through the conductor I equals NEA into EV tau divided by M into L. If you solve this relation, you will get current I is equal to ME square A V tau divided by M into L. So if we take potential difference V to the other side of the equation, then we can write I divided by V is equal to ME square A tau divided by M into L. If we reciprocate this relation, we can write V divided by L is equal to M into L divided by NE square A into tau. And as we know, the ratio of potential difference V to I is equal to resistance of the conductor. So resistance of the conductor can be written M divided by NE square tau, separate is constant, into L divided by A. So on the basis of drift velocity, the value of the resistance of a conductor provided by this relation. And student, this relation provides all the factors affecting the resistance of a conductor. From this relation you can see the resistance of a conductor. What is the first factor? That is internal factor of the resistance. The resistance of a conductor is directly proportional to its length. In this relation you can see resistance is directly proportional to length of the conductor, and resistance of the conductor is inversely proportional to area of cross section of the conductor. And the quantity written inside the bracket, this is actually resistivity of the material from which that conductor is made. So resistivity or specific resistance of the material of that conductor, rho, is this quantity written inside the bracket. So you can see resistivity is the characteristic of material. The rest of the quantities here, they are constant, either constant or depending on the external factor. For example, mass of electron for all the materials remains same. E, charge of electron. Tau, relaxation time. Relaxation time is dependent on the temperature of the material. N means resistivity of the material. Rho is inversely proportional to N. What is N? N is free electron density of that material. It means if free electron density is more, resistivity of the material is going to be less. So resistivity is inversely proportional to free electron density of the material. That is why we are saying resistivity is characteristic of the material, not of the conductor. Conductor is decided by all the three factors: resistivity, length of conductor, as well as area of cross section. But resistivity is decided by only one factor, that is free electron density of the material. And if temperature of the material rises, then due to decrease in the relaxation time tau, the resistivity will increase. So resistivity is directly proportional to temperature. With rise in temperature, resistivity of the material increases, but resistivity is inversely proportional to relaxation time. So we can write resistivity is inversely proportional to relaxation time, and relaxation time is inversely proportional to temperature of the material. So what is going to be the relation between resistivity and temperature? Resistivity is directly proportional to temperature of the material. So Ohm's law, derived by drift velocity theory, provides all the factors affecting the value of the resistance of a conductor. And this is Ohm's law. What is the conductance and conductivity of a material? So conductance is defined as the conductance of a conductor is the ease with which electric charge flow through that conductor, and it is equal to the reciprocal of the resistance. How easily electric charge can flow through a conductor after the application of potential difference? That measurement of that ease of charge flow through a conductor is defined as conductance. As resistance opposes the flow of charge, so conductance is the measurement of ease of charge flow, and its SI unit is ohm inverse or mho or Simon, written as capital S. So Simon is the SI unit of conductance. Similarly, conductivity of the material is defined as the reciprocal of the resistivity of a material is called conductivity. So as conductance is characteristic of a conductor, similarly conductivity is characteristic of the material of that conductor. So conductivity is equal to 1 by resistivity of the material. Conductivity is denoted by sigma. So sigma equals 1 by rho, where rho is resistivity. And you know, in the previous section we have seen the resistivity of the material is given by m divided by Ne squared tau. So what can be the conductivity of the material? Sigma is equal to reciprocal of this, that is Ne squared tau divided by m. And SI unit of the conductivity, as we know that SI unit of resistivity is ohm into meter. So if you reciprocate this, SI unit of conductivity is going to be ohm inverse into meter inverse. As we know, ohm inverse is Simon, so we can write SI unit of conductivity as Simon meter inverse would be the SI unit of conductivity of a material.